This is a brief introduction to bivariate distribution, which we also refer to as the joint distribution of two random variables. So we have got two random variables x and y defined on a probability space. When we so for suppose x represents height, y represents weight. Now when we look at them together as a vector, then we call it a two-dimensional random variable on the same space. And the joint distribution of xy is a probability statement of the following form, that x is in A, y is in B. Now A and B are two sets of real numbers, to be precise Borel sets of real numbers. So we are interested in probability statements like this. So we are making a joint statement on x and on y, and we want to compute the probability of both these events simultaneously. Here comma stands for and. And when we look at only the probability that x is in A or y in B, they are called the marginal distributions. In marginal distributions, we are computing the probability of one random variable at a time, being silent about the other. And in the joint distribution, we are looking at the, as the name joint suggests, that we are looking at the probability of an event where both x and y are involved. So if we know the joint probabilities, from there we can easily derive the marginal probabilities. So actually marginal probability is nothing but a joint probability where the second variable is unrestricted. Unrestricted in the sense that we are looking at all possible values of y while restricting x to A. Similarly, probability y in B is the event in terms of the joint distribution. It is the joint distribution where we are considering all possible values of x, restricting y to B. Now I have a question: what will be the probability that x is in R and y is in R? That is why I am considering all possible values of x and y. And similarly, another question is that what is the probability that x is in A but y is y is in a null set? Now to answer this question, you have to look back and see that x and y are random variables on the same space. That is, for every w in S, xw and yw are two real numbers. And what is the definition of xy? Xy at w will be xw and yw. So for when I say that what is the event that x is a real number, then y and y is a real number, well then for every w that is for the whole of S, and this will be satisfied, right? You take any w in S, then xw is a real number, yw is a real number. So this event actually represents what? And second thing is that if I take two events, two sets A and phi, what is the intersection of A and phi? So that is the hints. Now if I know that is what I am mentioning here. If I know all the joint probabilities, then I can find the marginal probabilities. However, the converse is not always true. That is, if I know the marginal probabilities, from there construction of the joint probabilities is difficult. Actually it cannot be done in general unless we make some assumptions, and one of the assumption is that of independence. So a pair of random variables are said to be independent if and only if. So it's an if. So if x the joint probability can be joint probability can be obtained from the marginal probabilities, and in fact the joint probability is the product of the two marginal probabilities. So independence of random variable refers to the fact that the joint distribution is the product of the marginal distribution. Now this concept of joint distribution can be made more specific in case x and y are either both two discrete or both continuous. So suppose x and y are two purely discrete distributions, the discrete random variables. That is, they take finitely or countably many values with probability 1. Then probability x equal to x, y equal to y is the probability of w's for which xw is equal to x intersection W's yw equal to y. So this is called the joint probability mass function of xy, and so they are just like your they're just like the probability mass function for discrete random variables. Like you have seen binomial distribution, Bernoulli distribution, Poisson distribution. So those are examples of univariate, or those are univariate discrete distributions, or discrete distribution of one random variable. And now in case this happens, that means when both x and y are discrete, so you can compute these joint probabilities as the sum of these individual probabilities, or the sum of the probability mass function, joint probability mass function. So this is also similar to the univariate case. That means when you have one random variable which is discrete and you know its probability mass function, then the probability that x is in a set is the sum of the probability mass function over the values in A. So same is the case when you have two random variables x and y. So in this case the joint probability is the sum over the values of x and y in the set A and B. Now this equation tells you that the order in which you add them does not matter. Similarly, if x and y are two continuous random variables, then there is a concept of joint density. So what is a joint density? A joint density is a non-negative valued function f such that you compute the probabilities by integrating this function. So always, whether univariate or multivariate, that does not matter. The density is a non-negative valued function integrating which you compute probabilities. So in this case, it is a function of two variables because there are two random variables involved. So if there are more random variable involved, you could have a multivariate density which is a function of several variables. But anyhow, since we are talking about two random variables here, so here the density, joint density function will be a function of two variables, and it is a non-negative valued function, and integrating this function you compute the probabilities. And in this case this joint density function is the if you integrate the joint density function over all the values of x and y, then you will get 1. And if you add, in the previous case, if you add all the value, this probability mass function over all the values of x and y, then also you will get 1. Now I have not written this here, but let me ask you, if you go back to this concept of joint density, so can you tell me what will happen when if x and y are two independent discrete random variables? In that case, what will be this joint PMF equal to? So a probability x equal to x intersection y equal to y. Can I express it as the product of the individual probabilities? Yes or no? Similarly, if I have two continuous random variables and f is a joint density function, then x and y are independent. That means that is equivalent to saying that the joint density function is the product of the density function of x and y. So then this fxy will be a product of a function in x and a function in y, and those functions will be the density functions of x and y. That will happen if and only if x and y are independent. So this is a brief introduction to the concept of bivariate distribution, independence, joint probability and joint density function. I'll give you some problems in the next lecture.